Okay, today we're doing the potentiometer principle experiment. So it's going to use the slide wire bridge, the big long wire with the meter stick that you also used in Wheatstone Bridge last week. And what you see right now is this diagram on top is just the basic idea of what we're doing. It's pretty straightforward. It gets more complicated after that. But what we're using it for is to measure the voltage of batteries. Last week, you used the slide wire bridge to get values of resistors, right? This time, we're going to get voltages of batteries with it. So the basic idea is, let's say there's your battery down there on the below the slide wire bridge, and it's connected to the galvanometer, and you've got the slide wire contact. Okay, let's say that current in the galvanometer is 0. I didn't write it there, but let's say it is. Well, the only way that can happen is if the voltage on the battery matches the voltage that's on that segment of wire from the left end to where the contact is. Okay, it would have to be, the voltage on the battery would have to be the same as the voltage on that section of the wire. Okay, that way they balance out and there's no current through the galvanometer. That's the idea. So for example, if the contact was at the 30 centimeter mark, for example, well, that would mean that 30% of whatever the total voltage was across the slide wire, 30% of that must be equal to the battery voltage. And so that's a way you can find battery voltage. Now, the reason you would bother to do this instead of just simply using a voltmeter, for one reason, it's very accurate. Okay. So whenever you measure the battery voltage with a voltmeter, it's actually going to use some current from the battery in order for the voltmeter to be able to read it. But in this case, there's no current being drawn from the battery once you've got it balanced. Maybe a little bit before you get it balanced, but ultimately there's no current being drawn from the battery, so it's a more accurate way to do it. Now what you see below, okay, this is basically what we're going to do with the battery conceptually. On the left is just a basic battery, okay? We're going to call it E, the voltage is E. What we're going to do is kind of refine our concept of the battery a little bit. We're going to make it a little bit more realistic. We've been treating power sources in this lab so far pretty much as if they always put out a constant voltage and that's all there is to it. But in reality, they do get loaded down a little bit when you connect something to them. The voltage across the battery or the power supply may drop a little bit. For practical purposes, for most things we've been doing so far, it doesn't really matter. But there are times in the real world when it does matter, and especially with a battery. So what you see here on the right is just a more specific concept of what a battery is like. What you have is that squiggly E, that cursive E symbol. That's the real voltage of the battery. That's the true voltage of the battery. And then you have an internal resistance of the battery itself. So we're basically modeling a battery as a true voltage minus a voltage drop across an internal resistance. Okay. So the measured voltage of the battery would be the EMF is what that's called. Okay. The true voltage is called the EMF, electromotive force, minus the voltage drop across the internal resistance. Okay, so why anybody would bother with this, why there's any reason to know about it, is because it might seem like, well, who cares about batteries, big deal, but in real world electrical applications, it is often important to know what the internal resistance of some power supply is and how that's going to affect things. So it does carry over. Okay. Okay, so now let's talk about the equipment you're going to use, the equipment. There are several things that are similar and you may get them confused. It's easy to do. There are several different kinds of batteries. There are a couple of possible unknowns that you might measure, okay? And they might look like just a regular D-cell battery, like this one, okay? So you might use a couple of those as your unknowns, all right? Or you might possibly use this hobby battery, okay? These are kind of old, and I don't think they even manufacture these anymore. But anyway, that's another possibility for an unknown that you might test out. Then there's also a known battery source that looks like this. It's basically just a AA, okay? But it'll have some number written on it like this one does. That's the voltage of this AA battery. We're going to treat that as a known voltage source. All right. Then there's also a special battery that it might look like this. It'll be just kind of a square box, or some of you will have one that looks like this, okay? Kind of a black metal box. So it could look like this, or it could look like this. But either way, it's what's called a high resistance battery, okay? So this is a special battery that you're going to use to get, you'll make some measurements to eventually get the unknown resistance and the electromotive force of it. Okay, so that's when they say high resistance battery, it doesn't look like a battery, it just looks like a box, but that's what they're talking about. Okay, there's also a double throw switch, and what that means is this, okay? So it's got a blade that can actually make contact two different places. So you can put it in a circuit and select to turn on different parts of the circuit at different times, okay? So it's going to have you use that. It's going to direct you to use that anyway. But if you want to take a shortcut and not use the switch and just take your banana plug wire and just plug in one place to another, that's really about as easy. So that's your choice. You can use this if it helps you to understand it better. But if you can take a shortcut and not use it and just plug wires in, that's perfectly acceptable as well. Some of them look older. You might get one that looks like this. These guys are kind of rough looking. They were made before you guys were born, maybe before I was born. So anyway, you might see a double throw switch. Okay. Let's see. And then there's a microammeter that looks like this. Okay. So that's going to come into play in part 3 of the experiment we do. Just measures microamps, analog meter. Now there's the galvanometer too. We're going to, like from last week, we're going to use that again. All right. Now the galvanometer looks similar to the microammeter, but don't get those confused. They are slightly different, and you use them differently. All right. And okay, so also should mention on your slide wire bridge, the big long meter stick with the wire, you're going to see a little white rectangular resistor attached to it. Last week in the Wheatstone bridge, you weren't required to use that. We probably told you not to use it. It may not have hurt anything if you did. But this time you do use that. You wire the power supply so that you are in fact including that little white rectangular resistor. Okay, so that'll be part of the circuit. That's the 4 ohm resistor in the schematic. It's just attached to the slide wire bridge. So do include that. It will be important to include it. It won't work so well if you don't. Okay, so do include that. And then one thing you should keep in mind too is polarity is going to be more important in this experiment. Most experiments we've been doing throughout the semester, it hasn't really mattered too much. You know, we didn't really worry about it too much. But in these circuits, you're going to have the power supply and the batteries connected with the plus and minus the way they do have them in the schematics, and it won't work if you don't. Okay. The other items like resistor boxes and so on, that doesn't really matter too much. But the batteries, you do need to have them with the minus and the plus connected exactly the way they have them in the diagrams. Otherwise, it won't work. So you'll have to keep that in mind. Okay, that's the equipment. So we're doing a report on this. We're doing a take-home report. There's a couple of graphs that you do. We want you to do them on graph paper by hand. And I probably ought to warn you a little bit. This could take a little bit of time. The experiment itself may actually run a little shorter than some other experiments we do. It's not as long as some other experiments we do. Once you get going on it, when you get the big circuit connected, doesn't take all that much time. But the report may take some time. There's quite a bit of analysis on it. You do these two graphs, you take slope and intercept, you get some information from those, and the questions that are assigned, they kind of guide you through an analysis of what's going on. It's kind of neat the way it works out when you actually get into it. But anyway, it does take some time, so don't wait till 15 minutes before lab starts next week to start on it, or it's not going to work so well for you. So you might want to set aside a couple hours to do this one. May take a little time. All right, so I'll let you get to it.